All right, another important concept is that of a linear combination. A linear combination of the set Vk, where k1 runs from 1 to r of vectors, is a sum of scalar multiples of these vectors. All right, so I could say okay, and that would be a linear combination of these vectors in my set. All right. The term span of this set of vectors is the set of all linear combinations of these vectors in this set. All right? Now, one important fact to recognize is that span is always a vector space. Span is always a vector space. How would we establish that? Well, if I had two vectors x and y, in this span, then I can imagine adding them together. Using the commutative, associative, and distributive properties, it's pretty clear that this sum could be rewritten in this way. Now, CK and DK are all elements of my field. Therefore, because the field is closed under addition, CK plus DK is also an element of my field for every single K. So that means that this is another linear combination of the vectors in my set. So the sum of any two vectors in this span is also in the span. What if I did a scalar multiple of one of my vectors in the span? Well, if I multiplied by d, I could say d times x, once again, using the distributive property, and then the associative property for scalar multiplication, I would have that. Since D and CK are elements of my field, for each K, D times CK will also be an element of my field. And therefore, this is another linear combination of my V vectors. So, span is closed under scalar multiplication. All right? Do I have an additive identity? Well, it's fairly obvious that if I choose CK equal to 0 for all K, then I'm just doing 0 times each of the vectors and adding them up. And you could go back through the axioms and see why it must be the case that that is equal to the 0 vector. So you can always get the 0 vector, and then it's fairly obvious that you can get additive inverses. What we're basically doing is we're piggybacking on the properties of the field, right? All of the elements of the field have additive inverses. So if I made dk the additive inverses of ck, and I add these all together, we can rearrange the terms using the commutative property, use the distributive property to make the sums take place in the field. And then the fact that these are the additive inverses of those would imply that we end up getting this linear combination where all the C's are 0. Okay? Now, by the way, the C's, the scalars in the linear combination, are called weights. Weights. All right, called its weights. Now, the trivial linear combination is that with all weights equal to 0. Okay? All the weights equal to 0. We said that that was an obvious way to get the 0 vector. All right? All right, so we've got all this business, span, always a vector space. Okay? So we can ask, how is this set related to the vector space that it spans? So we say, if a vector space is equal to the span of a set of vectors, This set of vectors is called a spanning set. For V. Okay? Spanning set for V. Now let's go back to our set space of polynomials of degree 2 or less. So what do you guys think? Does this represent a spanning set for T2? Well, the question would be, can I get an arbitrary element of P2 as a sum of scalar multiples of these 5 vectors? So what I could say is, I've got these, and I want to add them all together and see if I can make an arbitrary polynomial of degree 2 or less. All right? So for example, I could try to get that polynomial. Now, of course, our instincts indicate that the way that we should go about solving this is by distributing the C's and then combining like terms, right? So we would end up getting 2C1 plus 3C3 plus C4 T squared plus 4C2 plus 2C4 plus 4C5 T plus 3C1 minus C3 minus 3C4 minus 7C5. All right, and we would get this annoying combination. But the standard thing that people will do is they'll say, if I want this combination to give 7t squared plus 9t plus 13, then I'll set C1 plus 3 plus C4 equal to 7. 4c2 plus 2c4 plus 4c5 equal to 9. And this combination equal to 13. That's the standard thing that we would do. But why is that? Why would this follow? If I was trying to make this linear combination equal to 7t squared plus 9t plus 13, why then I can say that this has to be 7, this has to be 9, and that has to be 13? What we're doing there is we're making an argument based on these elements here, t squared, t, and 1. Saying if this is equal to that, then A must equal 7, B must equal 9, C must equal 13. Why is that the case? Well, if I subtract I would get that. All right? And so effectively what we're saying is that the only linear combination of t squared, t, and 1 that gives 0 is the one where the weights are 0. The trivial linear combination. All right? If that's true, if the set, or if the only way to get the 0 vector is the trivial linear combination, then the set is said to be linearly independent. Okay? So what we're looking at here is whether or not we can get every vector in P2 as a linear combination of these 5. Clearly, we can get every vector in P2 as a linear combination of just t, t, and 1. So it seems like we don't need all of these. Does that make sense? All right? So let's see if we can find an easier way to look at this. Okay, clearly we can get every vector here in terms of this set. How do I know that? Well, from here, I can always get t. If I called these vectors v1, v2, v3, v4, and v5, I could say t is equal to 1/4 v2. Right? And now, if I add v1 and v4 together, I'll get t, or I'll get 3t squared plus 2t. Right? And so that will allow me to get t squared. So I could say t squared is equal to 1/3 v1 plus v4, and then minus 2t. Everybody see that? Oh, this is v2. All right? So that gives me t and t squared. I've involved so far vectors 1, 2, and 4. If I look at vector 3 or vector 5, I can get 1 from either of those. So for example, if I did v5, that's equal to 4t minus 7. So that's v2 minus 7. So that means that one-seventh of v2 minus v5 is equal to 1. All right, so what have we used so far? 1, 2, 4, and 5. It's kind of interesting. We haven't used 3. But clearly we can get v3 in terms of these other ones. So we've got some interesting relationship here. There's a way to write v3 in terms of the other vectors. Stated another way, v3 is already in the span of those vectors. I don't need to include them separately. Okay? Since I can get t, t squared, and 1, I can clearly get any vector in P2. So this does represent a spanning set, but it's kind of too big. It contains too many elements. I don't need this many. We just saw I didn't need V3. Let's see if we can write down the most general possible vector in our set. So I would have a t squared plus bt plus c times 1. That's the most general vector in our set. Okay? And so, if I wanted to, I could distribute and write all this out in terms of the v's. So I could have 1/3 A, that's the v1. What about the v2? So it's going to be minus 2/3 A plus 1/4 B plus 1/7 C. All right? minus 2/3 A. Oh, wait.
Minus one.
No, minus 1/6.
Okay.
All right? And then plus 1/7 C. And then I've got V4. So that's A over 3 V4. What a mess. All right. So the key to all this lies in recognizing that I can write t squared, and 1 in terms of these vectors. Since t squared, and 1 all certainly do represent a spanning set, the fact that I can write t squared, t, and 1 in terms of some combinations of these vectors implies that these guys do span. But as I said, I'm keeping too many of them. All right, I can actually span with only 3. All right, there's too many of them. I can actually span with only 3. There are ways that I can get 0. Okay? So one way that we can look at this, we said that we can get 0. We can write this one in terms of the other ones. All right? So let's see if we can find an easy way to get 0. All right? So let me just, all right, I'm going to cut that off. We went way too far down that rabbit hole. Okay? The crux of this is that a set is called linearly independent if the only linear combination giving 0 is the trivial combination. All right?